Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever for linear modeling part 2. So, let's get to it, shall we? First part we are going to talk about is the line of best fit, which I know you've heard of before. The line of best fit basically is a line that, given a set of data points, if you draw that line, it's the best possible representation of all of the data. Okay, and we can eyeball it, or we can do it using mathematics, or using, well, it's all mathematics really, or using something called linear regression. And we're going to talk about all of that in this video here. So, let's take a look at this quick example. We have an athlete, age in years, and the distance thrown of the discus. This is the opening problem from this unit. And we have all the data points, and we can draw a line of best fit. Well, here's a method to do so. We can calculate the mean of all of the x values and all of the y values, and we mark that mean point on the scatter diagram, or the scatter plot. That looks to be this point right here, 12, 20. And then we draw a line through the mean point, which fits the trend of the data, so that about the same number of data points are above the line as below it. So that's just an eyeball test. So you find the mean of both x and y, plot that point, and draw a line through that mean that you think is the line of best fit. So that's one way to approach it. So for the opening problem, the mean point is 1529. Oh, so that wasn't it there before. Sorry about that. So the mean is 1529. So to draw the line of best fit through 1529, and it's a bit of an estimate. We want to try and have the same number of data points above and below. So for an example, consider this set of data. Mass and length for mass on a spring. So if we have a mass of 0, the length of the spring is a mass of 0 grams. The length of the spring is 17.7 centimeters. If there's 50 grams attached to the spring, then the spring stretches to a length of 20.4 centimeters, and so on. So it says draw a scatter diagram for the data and draw a line of best fit incorporating the mean point. Well, I'm not going to do that. I'm just going to cut out the answer they had in the book. So all the data points are there. The mean of the masses in the experiment is the average of all of these, which clearly, hopefully, you can just look at it and see, well, that would be 125. And the mean length of the spring is 23.15. So that point is plotted. And then a line is drawn. I don't know if this would be your line, or if it would be the line that you would draw, but a line is drawn here as, just using the eyeball test as best as possible. Then part B says find the equation of the line you have drawn. Well, they estimate that the point, you just need 2 points to find the equation of a line, yes? So they say the point 226, well, it's not an estimate, we have it right here, is on the line. And then using that, they find the equation of a line, which in y equals mx plus b form comes out to be the length is approximately equal to 0.04 w plus 18, where 0.04 is the gradient or slope, and 18 would be the y-intercept. Well, we know it's 17.7, but you can see how it worked out, and it's off a little bit because of of the mean there. Okay. Now, I also wanted to show you. Well, no, that's eyeballing it. Now, the least squares regression line. Now, this is an actual mathematical calculation that we're going to do, and that's by linear regression. So what that is, it's a method that you will not have to do by hand. We will use the calculator But what it does is it reduces the distance from all the points to a line. It finds a line that is the least distance of the square of the vertical distances from that line. And that's called the least squares regression line. And we are going to do it using a calculator. Okay, for example, use technology to find the least squares regression line for the mass on a spring data. So it's the same problem that we did before, but we're going to do it using a calculator. Okay, so I have already entered in the data. You already know how to get a spreadsheet, yes? And I've got all the data in there so you can see. And it's very simple how to find the least squares regression line. But before we do that, I'm going to show you how to graph a scatter plot so we can actually see the graph of this line. So what we're going to do now is add a page, plus page, and we're going to add a graph. Okay, and so they put it on 1.2. And then we're going to change menu, graph entry edit, and we want it to be a scatter plot. Okay, and so for x, that's a variable. I'm going to click the variable key. And the x value was mass, right there. And the y value is, come on, go down there, tab. Okay, back to var, is length. And I hit enter, and you see nothing. Well, if you remember, the scale of this graph is not going to show those scatter plots, so what we're going to do is go to menu, window zoom, and zoom data. Boom goes the dynamite. There's all our data right there. Okay, so now back to here. Let's find the use regression to find the line of best fit. So we're going to go menu, back to the spreadsheet, statistics, stat calculations, linear regression, and it doesn't, we're going to put it in the form, this is what you should probably always use, either 3 or 4, this one or this one will work, but this puts it in gradient intercept form, y equals mx plus b. So I'm going to click that, okay, and then I have to choose my x list again, and remember that's mass. My y list is length. And this is going to save the equation as the function f1, and we're going to be able to graph it. Frequency list, don't worry about. And the first result, it's going to put it in column D, so that's cool. And we're going to click OK. And boom goes the dynamite. Okay, and I'm going to make this a little bigger, I think. Let's see if I can make this so we can see it. Okay. So here, it's in the form mx plus b. It gives us m, 0.0040, rounded to 3 sig figs, and b is approximately 18.1. What is our Pearson coefficient? It's pretty strong correlation, 0.99, very close to 1. Okay, so if we go back, or if we go to our graph now, we can graph that line, and we'll see the equation. I just need to change the graph back, menu, graph entry or edit, and I need to go back to function. Okay, and the calculator, if you arrow up, it has put it in function 1, remember 0.04 and 18.12, but it puts everything it knows in there. We hit enter, and it graphs that line of best fit. Okay, so back to the problem, it said, what, pray tell, is that line of best fit? What's the equation of that line of best fit? I'll click right here, and that turned out to be, let's see, the length is approximately equal to 0.04 W plus, and our y-intercept was, what was it, 18.1? Yeah, about 18.1. Okay, and if you compare that to what we estimated, we weren't too far off on our estimation, or at least they weren't, 0.004 plus 18. Okay, interpolation and extrapolation. This is the last topic for this chapter. If we have a bunch of data and which we have here. And we want to find out the y value for an x value that is not one of these points, that doesn't have an x value for one of these points. We can either interpolate or extrapolate. And the way we do that is we consider the lower pole, which is the data that has the least x coordinate, and the upper pole, which is the piece of data that has the greatest x coordinate. If we are going to use an x value between the lower and upper pole, we are interpolating. If we are going to the left of the lower pole or to the right of the upper pole, then we are extrapolating the data. And as a general rule, it's reasonable to interpolate between the poles, but it's not as reliable, it's unreliable to extrapolate outside the poles. So how do we do that? Okay. So here we have a table that shows how far a group of students live from school and how long it takes them to travel there each day. So someone lives 7.2 kilometers away from school, it takes them 17 minutes, and so on. Draw a scatter diagram or scatter plot of the data. I know you can do that, and you should be able to do it by hand, just in case they ask you. I'm going to go back to the calculator where I have entered the data already. Let me scroll down so you can believe me. Oops, there we go, all the way down. And let's go ahead and add a page, and we'll draw the scatter plot that way again, just so you can see how that's done. So we're going to add a graph, and then we're going to say menu, graph entry edit, scatter plot, our x, let's see, so this time for vars we are, oh, it has all kinds of stuff. It was distance is our x variable, and then we'll tab over to the y coordinate, and oops, not menu, I hate when I do that. Here, hit escape, var, and it is travel distance, or travel, this one right here, travel time I put in there. And I'll hit enter, and then I will go to window zoom, and zoom data, zoom data, and there we go, distance versus travel time. Then we'll go back and find our line of best fit using technology. So again, we'll do menu, stats, stat calculations, linear regression, mx plus b, bam, we got to choose our x, which is distance, our y, which is travel time. I had abbreviated the travel. You won't have this much stuff in your calculator. It's just because I'm doing stuff. It's going to save our regression equation into the second function, and let's see where it's going to start our data. This is it's going to give our first result in column D, which is good because we don't want it to overwrite what we have already put in column A and column B. So we're going to hit OK. There she blows. Here, let's move this over a little bit so we can get a better view of it, and then I'll move this, drag a little bit. And we can see that our gradient or slope is 2.16 and our y-intercept is about 1.42. Let's see what our Pearson coefficient is, a very strong correlation. So I'm going to go to the graph now, and I'm going to change it back to function, and arrow up to F2, and there it is, graph it, and there's my line of best fit. F2 of x equals 2.16x plus 1.42. Okay, so let's go back. I want to get a picture of that and put it on where we can talk about it. Okay, oops. Okay, now moving it. Okay. So now estimate how long it takes Pam to travel to school if she's 15 kilometers from school. Well, all we have to do is replace x with 15 and work that out. 2.16 times 15 plus 1.42, I will tell you, is approximately equal to 33.8. So let me do this. So if I put this with 15, That's approximately equal to, what did I say, 33.8. Okay, and comment on the reliability of our estimate. Well, it's very reliable because we saw that R was equal to 0.99. So that's a very strong correlation. And that holds true with the line that we see here. The data is all clustered around that line. And the last thing I want to show you, because this could come up, we could find that out pretty easily if we do, let's see, geometry and points and lines, and we do point on, and we do a point on the line here. Okay, and let's hit escape. And then if I double click in there and change that x coordinate to 15, that's another way to find that it would take Pam 33.8 minutes to, or no, that she lives 33.8. Oh yeah, 33.8 minutes it would take her to get to school instead of having to do the calculation right there. Okay, I have yammered on enough. Sorry about the length, but that is the end of this section. We will see you next time as we go out to the great REM. See ya.